Tonight, we're going to explore something that sounds straightforward, but turns out to be one of the strangest events in all of physics. What happens when a photon meets an atom? Because here's what most people picture. A tiny ball of light slamming into a tiny ball of matter, like two marbles colliding. But that's not what happens at all. What actually happens is far more bizarre. A photon can vanish completely inside an atom, as if it never existed. It can kick an electron out of the atom entirely. It can bounce away with less energy than it arrived with. Or it can pass through as if the atom isn't even there. The outcome depends on something so precise, so specific, that it reveals one of nature's deepest secrets. And by the end of this, you'll understand exactly why. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something that seems completely obvious. Light hits things. You see it every day. Sunlight hits your skin and you feel warmth. A flashlight beam hits a wall and you see a bright circle. A laser pointer hits a surface and you see a dot. Light arrives, it hits something, and something happens. Simple. Except it isn't simple at all. Because when you zoom in far enough, when you look at what's actually happening at the smallest possible scale, the whole idea of light hitting something falls apart. What actually occurs when a single particle of light meets a single atom is one of the strangest, most precisely governed events in all of nature. And understanding it changes everything about how you see the world around you. To understand this interaction, we first need to know what's showing up to the meeting. There are two players, the photon and the atom. Let's start with the photon. A photon is a single particle of light, but calling it a particle is misleading. It's not a tiny ball or a speck of glowing matter. A photon has no mass whatsoever. It's a packet of electromagnetic energy that travels through space at the speed of light, about 300,000 kilometers per second. Every photon in the universe travels at this speed. No faster, no slower. From the instant it's created to the instant it is absorbed, it moves at exactly light speed. It never stops. It never slows down. It simply is, from the moment it begins, moving at the fastest speed the universe allows. Now, here's what matters for our story. Every photon carries a specific amount of energy determined by its frequency. Higher frequency means higher energy. Lower frequency means lower energy. Each photon has one energy, locked in from the moment it's created. A photon of red light carries less energy than blue. Ultraviolet carries more than either. X-rays carry far more, and gamma rays carry the most of all. The energy of a photon is, in a very real sense, its identity. Two photons with the same energy are identical. There is no way to tell them apart. And this energy, this specific precise quantity that each photon carries, is going to turn out to be the single most important factor in determining what happens when that photon encounters an atom. Now, let's talk about the other player, the atom. An atom is the basic building block of ordinary matter. Everything you can touch, see, taste, or smell is made of atoms. Your body, the air you breathe, the screen you're looking at, the ground beneath your feet. All of it is atoms. An atom consists of a nucleus at the center, made of protons and neutrons packed tightly together, and electrons that exist around that nucleus. The nucleus is incredibly small compared to the atom itself. If an atom were a football stadium, the nucleus would be a marble at center field. The electrons would be somewhere out in the stands, occupying the vast space around that tiny core. But here's where atoms become truly strange. The electrons around the nucleus can't orbit at any random distance. They are restricted to specific energy levels. Think of these levels like the rungs of a ladder. An electron can stand on the first rung or the second rung or the third, but it cannot stand between them. There is no halfway point. The electron is either on one rung or another, never in between. This isn't a metaphor. It's how atoms actually work. The energy levels are quantized, meaning they come in specific discrete values determined by quantum mechanics. Each type of atom has its own unique set of energy levels, its own ladder with rungs spaced at particular intervals. Hydrogen has one pattern, helium has a different pattern. Every element on the periodic table has its own unique arrangement. And this uniqueness, this fingerprint of energy level spacing, is going to be critical to our story. Now, under normal conditions, the electrons in an atom occupy the lowest energy levels available to them. This is called the ground state. It's the atom's default configuration, the most stable, most comfortable arrangement. The electrons are sitting on the lowest rungs of the ladder, and they'll stay there unless something comes along and gives them a reason to move. And that something is a photon. This is where the real story begins. The part that most people never learn. What actually happens when a photon arrives at an atom? Because the answer is not what you'd expect. It's not a collision. There's no impact, no crash, no bounce in the way you'd imagine two solid objects meeting. What happens instead is something far more subtle and far more profound. It's an energy negotiation. A photon arrives carrying a specific amount of energy. The atom has a specific set of energy levels its electrons can occupy. And what happens next depends entirely on whether those two things match. Let's take the simplest case first. Imagine a hydrogen atom sitting in its ground state. Its single electron is on the lowest rung of the energy ladder. Now, a photon comes along. This photon is carrying some amount of energy. The question is, does that energy correspond to the exact difference between the electron's current energy level and one of the higher energy levels in the atom? If the answer is yes, something remarkable happens. The photon is absorbed. It doesn't bounce off. It doesn't pass through. It ceases to exist. The photon vanishes completely, and all of its energy is transferred to the electron. The electron uses that energy to jump from its current rung to a higher rung on the ladder. The atom is now in what physicists call an excited state. It has more energy than it did before. The electron has climbed higher on the ladder, and the photon that lifted it there is gone, destroyed. It no longer exists anywhere in the universe. This is absorption. A photon dies and an electron jumps. But here's the catch. And this is the crucial part that makes this whole process so strange and so specific. The photon's energy has to match the gap between energy levels almost exactly. Not approximately, not close enough. The energy must correspond to an allowed transition in the atom's energy level structure. If the photon is carrying slightly too much energy or slightly too little, the atom simply cannot absorb it. The transaction fails. The photon continues on its way as if the atom weren't even there. Let me try to make this concrete. Imagine you're standing at the bottom of a staircase. Someone is throwing balls at you, and each ball represents a photon with a certain amount of energy. The rule is that you can only catch a ball if its energy is exactly the right amount to lift you from the step you're currently standing on to one of the specific steps above you. If a ball arrives with exactly the energy needed to get you from step 1 to step 2, you catch it and you jump to step 2. If a ball arrives with exactly the energy to get you from step 1 to step 3, you catch it and you jump to step 3. But if a ball arrives with energy that would put you between steps, between step 2 and step 3, for example, you can't catch it. That in-between position doesn't exist. There's nowhere for you to go. So the ball passes right through your hands as though you weren't there. The atom can't accept that photon because there's no energy level for the electron to land on. This is one of the most important principles in all of quantum physics. Energy exchange between photons and atoms is not a free-for-all. It's a highly selective process governed by the specific energy level structure of the atom. Each type of atom has its own unique set of allowed transitions, its own specific set of photon energies it can absorb. Hydrogen absorbs photons at certain very specific energies. Helium absorbs at different energies. Sodium absorbs at its own set of energies. Every element has a unique absorption pattern because every element has a unique arrangement of electron energy levels. This was one of the great puzzles of early 20th century physics. Scientists had known since the 1800s that when you pass white light through a gas, certain colors go missing. You see dark lines in the spectrum, specific wavelengths of light that have been removed. In 1814, a German optician named Joseph von Fraunhofer was studying sunlight when he noticed hundreds of dark lines in the solar spectrum. He carefully mapped and catalogued them. Some were faint, barely visible. Others were strikingly dark and prominent. He labeled the most visible ones with letters A through K and beyond, carefully mapping their positions without knowing what caused them. These became known as Fraunhofer lines, and they puzzled scientists for decades. What was causing these gaps in the sunlight? The answer came gradually. In 1859, Gustav Kirchhoff and Robert Bunsen demonstrated that each chemical element produces its own unique set of spectral lines. When you heat an element until it glows, it emits light at very specific wavelengths. Fraunhofer's mysterious D lines turned out to belong to sodium. His C and F lines belonged to hydrogen. His K line was calcium. And when you pass white light through a cool gas of that same element, it absorbs light at those exact same wavelengths, creating dark lines in the spectrum. The bright lines an element emits and the dark lines it absorbs are the same. They're the fingerprint of that element. But it wasn't until 1913 that anyone could explain why. That's when the Danish physicist Niels Bohr proposed his model of the atom. Bohr suggested that electrons orbit the nucleus only at specific allowed distances, each corresponding to a specific energy level. When an electron jumps from a lower level to a higher level, it absorbs a photon whose energy equals the difference between those levels. When it drops back down, it emits a photon with that same energy. The specific energies involved, and therefore the specific wavelengths of light absorbed and emitted, depend on the unique structure of each atom. This was a revolutionary idea. It explained the spectral lines that had puzzled scientists for decades, and it revealed something profound about the nature of atoms. They don't interact with light randomly. They interact with surgical precision, absorbing only photons whose energy matches their internal architecture. Let me give you a specific example to make this tangible. Hydrogen, the simplest atom, has a very well-studied set of energy levels. The gap between the first energy level and the second energy level in hydrogen requires a photon with a wavelength of about 121.6 nanometers. That's in the ultraviolet part of the spectrum, invisible to human eyes. The gap between the first and third level requires a photon at about 102.6 nanometers, deeper ultraviolet. The gap between the second and third level corresponds to about 656 nanometers. That's red light, visible red light. This particular transition from the second to the third energy level produces a spectral line called H-alpha. It's one of the most famous spectral lines in all of astronomy because it shows up everywhere. In nebulae, in the atmospheres of stars, in the gas between galaxies. Whenever you see a photograph of a glowing red nebula in space, you're seeing H-alpha emission. Hydrogen atoms absorbing energy and then releasing photons at exactly 656 nanometers. That specific shade of red is the signature of hydrogen doing one very specific thing. An electron jumping between two very specific energy levels. And here's what makes this even more powerful. Because every element has its own unique pattern of energy levels, every element produces its own unique set of spectral lines. This means that by analyzing the light from a distant star, astronomers can determine exactly what elements are present in that star's atmosphere. They don't need to travel there. They don't need to collect a sample. They just need to study the light. The dark absorption lines in a star's spectrum tell you precisely which atoms are present and which photons those atoms swallowed on the light's journey from the star's surface to your telescope. This is how we know what stars are made of. This is how we know that the sun is mostly hydrogen and helium. This is how we discovered helium in the first place. In 1868, during a solar eclipse, astronomers noticed a spectral line in the sun's light that didn't match any known element on Earth. They named the unknown element helium after Helios, the Greek god of the sun. It wasn't found on Earth until nearly 30 years later. We discovered an element on the sun before we found it on our own planet, all because of how photons interact with atoms. This selective absorption also explains something you experience every single day, but probably never think about. Why are things the colors they are? When white light, which contains all wavelengths of visible light, hits an object, the atoms in that object absorb photons at certain wavelengths and reflect or transmit the rest. A red apple appears red because the atoms and molecules in its skin absorb most wavelengths of visible light except red. The red photons are the ones that bounce back to your eyes. A blue shirt appears blue because it absorbs most wavelengths except blue. A leaf appears green because the chlorophyll molecules in it absorb red and blue light very efficiently, but reflect green. Every color you see in the world around you is the result of atoms selectively absorbing certain photons and letting others go. The colors of your life are determined by the energy level structures of atoms and molecules. Think about how astonishing that is. Every time you look at a sunset, you're watching trillions upon trillions of photons being selectively absorbed and scattered by atoms and molecules in the atmosphere. Every time you admire a flower, you're seeing the result of specific molecules absorbing specific photon energies and reflecting the rest to your eyes. The beauty of the natural world, the colors of autumn leaves, the blue of the ocean, the red of a rose, all of it comes down to this one interaction. Photons meeting atoms, and atoms deciding which photons to absorb based on their internal energy level structure. But let's go back to the atomic level for a moment. Because there's another aspect of absorption that's important to understand. When an atom absorbs a photon and its electron jumps to a higher energy level, the atom is now in an excited state, and excited states are unstable. An atom doesn't want to stay excited. It wants to return to its ground state, to its lowest energy configuration. Think of it like holding a ball above your head. You can do it, but it takes energy to maintain that position. Eventually, your arms get tired and you let the ball drop. Similarly, an excited electron will eventually drop back down to a lower energy level. And when it does, it releases the extra energy. But that's the next stage of this journey, and we'll get there soon. For now, what matters is this fundamental principle. An atom in its ground state is a selective absorber. It will absorb only those photons whose energy corresponds to the exact difference between its current electron energy level and a higher allowed energy level. Everything else passes through. This is not like a wall blocking a stream of water, where everything gets stopped regardless of its properties. It's more like a lock that only accepts certain keys. The photon's energy is the key. The atom's energy level spacing is the lock. If the key fits, the photon is absorbed and the electron jumps. If the key doesn't fit, the photon continues on as if the lock weren't there. This precision has consequences that stretch far beyond the laboratory. It means that the universe is not opaque to all light equally. Different wavelengths of light can travel vastly different distances, depending on what atoms lie in their path and whether those atoms happen to have energy levels that match. A photon of visible light might travel unimpeded through a cloud of hydrogen gas because its energy doesn't match any of hydrogen's allowed transitions from the ground state. But a photon of ultraviolet light at exactly the right energy would be snatched up immediately, absorbed by the first hydrogen atom it encountered. This is why our atmosphere is transparent to visible light, but blocks most ultraviolet. The molecules in our atmosphere, primarily nitrogen and oxygen, have energy level structures that happen to allow visible light to pass through while absorbing much of the ultraviolet. If those molecules had slightly different energy levels, if the rungs on their ladders were spaced differently, our atmosphere might be transparent to ultraviolet and opaque to visible light. We would live in a world where we couldn't see the sun directly, but could see in ultraviolet. The fact that we see in visible light is not a coincidence. Our eyes evolved to be sensitive to the wavelengths of light that our atmosphere happens to transmit most efficiently. The transparency of air to visible light is a consequence of atomic energy level structure, and our biology adapted to take advantage of it. Let me bring this back to the fundamental point. When a photon meets an atom, the outcome is not random. It's not chaotic. It's not like two billiard balls colliding where the result depends on angles and speeds. The outcome is determined by one thing above all else. Does the photon's energy match an allowed transition in the atom? If it does, the photon is absorbed and the electron jumps to a higher state. The photon ceases to exist. Its energy lives on inside the atom, stored as the elevated state of an electron. If the energy doesn't match, the photon is ignored. It passes through the atom's space and continues on its way, unchanged and unaffected, as if the atom were invisible. This is the first and most fundamental thing a photon can do to an atom. It can be absorbed, it can die, surrendering its energy to an electron and boosting that electron to a higher state. But this only happens when the conditions are exactly right. When the photon's energy fits the atom's quantum architecture like a key fitting a lock. The universe is built on this precision. The colors you see, the chemical reactions that sustain your body, the light from distant stars that tells us what the cosmos is made of, all of it traces back to this one astonishingly selective interaction. A photon arrives, an atom evaluates, and the answer is either yes at exactly this energy, or no, not at any price. There is no negotiation, there is no compromise. The rules are absolute, and they are written into the deeper structure of reality itself. So an atom has absorbed a photon. An electron has jumped from a lower energy level to a higher one. The photon is gone, destroyed. Its energy now lives inside the atom, stored in the elevated position of that electron. The atom is in an excited state, carrying more energy than it normally would. And this is where the next part of the story begins. Because the atom doesn't stay excited. It can't. Excited states are inherently unstable. The electron sitting on a higher rung of the energy ladder is like a boulder balanced on the edge of a cliff. It will hold for a moment, but not forever. Something is going to give. And when it does, the atom will respond in a way that is just as precise, just as governed by quantum rules, as the absorption that started the whole process. Let's think about what's happening inside the atom at this moment. The electron has been boosted to a higher energy level. It's sitting up there, holding onto energy it didn't have before. But quantum mechanics tells us that this situation is temporary. The ground state, the lowest energy configuration, is the natural resting place of the atom. It's where the atom wants to be. And so, after a very brief period, usually just a few billionths of a second, the electron drops back down to a lower energy level. And when it drops, it has to get rid of the extra energy. It can't just quietly slide down the ladder. Energy doesn't disappear. It has to go somewhere. And where it goes is into a brand new photon. This is spontaneous emission. The electron falls from a higher energy level to a lower one. And in the process, it creates a photon. A completely new photon that didn't exist a moment ago. This photon carries away exactly the amount of energy that corresponds to the gap between the two energy levels the electron jumped between. If the electron drops from the third energy level to the second, the emitted photon has exactly the energy of that gap. If it drops from the fifth level to the second, the photon has exactly the energy of that larger gap. The photon's energy, and therefore its wavelength and color, is determined entirely by which two rungs the electron jumps between. This is the reverse of absorption. In absorption, a photon dies and an electron climbs. In emission, an electron falls and a photon is born. The two processes are mirror images of each other, and they involve the exact same energy levels and the exact same photon energies. If a hydrogen atom absorbs a photon at 656 nanometers to boost its electron from the second level to the third level, then when that electron falls back from the third level to the second, it emits a photon at exactly 656 nanometers, the same wavelength, the same energy, the same color. This symmetry is one of the most elegant features of quantum physics. The energy levels of an atom determine both what it can absorb and what it can emit, and those two sets are identical. But here's something important that most people don't realize. When the atom emits this new photon, the photon doesn't have to go in the same direction the original photon came from. The incoming photon might have been traveling from left to right, but the emitted photon can fly off in any direction. Up, down, sideways, backward, any direction at all. The emission is random in terms of direction. The atom doesn't remember where the original photon came from. It just releases the energy as a new photon that shoots off in whatever direction quantum chance dictates. This seemingly small detail has enormous consequences. Think about what happens when sunlight passes through a gas. Photons of specific energies get absorbed by atoms in the gas. Those atoms get excited, and then, very quickly, those atoms emit new photons at the same energies. But the emitted photons go in random directions. The original beam of sunlight was traveling in one direction, say from the sun toward a telescope. The absorbed photons are removed from that beam. The emitted photons are scattered in all directions, and only a tiny fraction of them happen to continue in the original direction toward the telescope. The result is that the beam of light arrives at the telescope with dark lines at the wavelengths that were absorbed. The photons at those wavelengths were grabbed by atoms and then re-emitted in random directions, effectively removed from the original beam. This is how absorption lines form in stellar spectra. The photons aren't truly destroyed forever. They're re-emitted. But they're re-emitted in random directions, so they're lost from the original line of sight. Now, there's another subtlety to emission that makes it even more interesting. The electron doesn't always fall back down in one single jump. Remember the energy level ladder. If an electron has been boosted to, say, the 5th energy level, it doesn't necessarily drop all the way back to the 1st level in one go. It can come down in steps. It might drop from the 5th level to the 3rd level, emitting one photon. Then from the 3rd level to the 2nd level, emitting another photon. Then from the 2nd to the 1st, emitting a 3rd photon. Each of these steps produces a photon with a different energy, a different wavelength, a different color. And the total energy of all those photons combined equals the energy of the single photon that was originally absorbed. Energy is conserved. It has to be. But instead of one high energy photon going in and one high energy photon coming back out, you get one high energy photon going in and multiple lower energy photons coming out. The energy is the same, but it's been split into smaller pieces. This cascading process is the secret behind one of the most beautiful phenomena in everyday life. Fluorescence. You've probably seen fluorescent materials without knowing what was going on at the atomic level. Black light posters that glow vivid green and orange under ultraviolet lamps. White clothing that seems to glow brighter than it should under certain lighting. Laundry detergents that make your white shirts look almost blue-white in sunlight. Fluorescent minerals that glow spectacular colors in museum displays. All of these work because of cascading emission. Here's what happens. An ultraviolet photon, which is invisible to your eyes, is absorbed by a molecule in the fluorescent material. That ultraviolet photon has high energy because ultraviolet light has a shorter wavelength and higher frequency than visible light. The molecule absorbs this photon, and one of its electrons jumps to a high energy level. But instead of emitting a single ultraviolet photon, when the electron drops back down, the electron cascades. It drops in steps, losing a little energy at each step, as heat or vibration within the molecule. And then it makes a final large drop, emitting a photon of visible light. The emitted photon has less energy than the original ultraviolet photon, because some energy was lost to heat during the cascade. Less energy means longer wavelength, and longer wavelength means the photon has moved from the invisible ultraviolet range into the visible range. You've taken invisible light and converted it into visible light. The material appears to glow. This is why things look so vivid under a black light. The black light emits invisible ultraviolet. When that radiation hits a fluorescent material, the material absorbs those invisible photons and re-emits visible ones. The material seems to glow with its own light, and in a sense, it's converting energy you can't see into energy you can. This also explains why certain materials seem brighter than they should be in sunlight. A white shirt treated with fluorescent brighteners absorbs some ultraviolet from sunlight and re-emits it as blue-white visible light. The shirt ends up reflecting more visible light than actually arrives in the visible range. It does mining invisible energy from sunlight and converting it into visible glow. Fluorescence is fast. The emission happens within billionths of a second after absorption. There's a related phenomenon called phosphorescence that works on the same principle, but much slower. In phosphorescent materials, the excited electron gets trapped in an intermediate state it can't easily escape. It lingers there, sometimes for seconds, sometimes for hours. Then it finally drops down and emits a visible photon. This is why glow-in-the-dark toys work. You charge them by exposing them to light, trapping electrons in intermediate states. Turn the lights off, and those electrons slowly release their stored energy as visible photons, gradually fading. Now, everything I've described so far is spontaneous emission. The electron drops on its own without any outside trigger. It falls when it's ready, which in most cases is within nanoseconds. But there's another kind of emission that's fundamentally different and far more important for technology. It's called stimulated emission, and understanding it requires us to think about what happens when a photon encounters an atom that's already excited. Picture this. An atom has already absorbed a photon. Its electron is sitting on a higher energy level. The atom is excited, holding extra energy, waiting to release it. Now, a second photon comes along. This second photon has exactly the same energy as the gap the electron is waiting to fall across. In spontaneous emission, the electron would eventually drop on its own and emit a photon in a random direction. But the presence of this second photon changes everything. The incoming photon stimulates the excited electron to drop immediately. The electron falls, and it emits a photon. But this emitted photon is not random. It's identical to the photon that stimulated it. Same energy, same wavelength, same direction of travel, same phase, meaning the waves are perfectly synchronized. Their peaks and troughs aligned. Where there was one photon, now there are two. Two perfectly identical photons traveling in the same direction, in perfect lockstep. This is stimulated emission, and it was first described theoretically by Albert Einstein in 1917. Einstein was studying the statistical behavior of photons interacting with atoms, and realized that absorption and spontaneous emission alone couldn't explain how light and matter reach thermal equilibrium. There had to be a third process, one where an existing photon could trigger an excited atom to emit an identical copy. The idea was elegant but seemed like a theoretical curiosity at the time. It took decades for anyone to figure out how to make it useful. The breakthrough came in the 1950s and 1960s. Scientists realized that if you could create a situation where many atoms were simultaneously in an excited state, a condition called population inversion, then a single photon passing through this collection of excited atoms could trigger a cascade of stimulated emissions. One photon stimulates an excited atom, producing two photons. Those two photons stimulate two more atoms, producing four. 4 become 8, 8 becomes 16. The number of identical photons grows exponentially, and all of them are traveling in the same direction with the same wavelength and perfectly synchronized phases. This is a laser. The word laser is actually an acronym. It stands for light amplification by stimulated emission of radiation. Every laser in the world, from the tiny laser in a barcode scanner to the massive lasers used in nuclear fusion research, works on this principle. You pump energy into a collection of atoms or molecules to create a population inversion, where more atoms are in an excited state than in the ground state. Then you let stimulated emission do its work. One photon triggers another, which triggers another, which triggers another, building up an intense beam of perfectly coherent light. The first working laser was built in 1960 by Theodore Maiman at Hughes Research Laboratories in California. It used a synthetic ruby crystal as the lacing medium. The ruby was surrounded by a flash lamp that pumped energy into the chromium atoms in the crystal, exciting their electrons. When enough atoms were excited, stimulated emission took over and the ruby emitted a pulse of coherent red light at 694.3 nanometers. It was a modest device by today's standards, but it demonstrated that stimulated emission could be harnessed in the real world. Today, lasers are everywhere. They're in your phone, they're in fiber optic communication systems that carry internet traffic across oceans. They read the data on DVDs and Blu-ray discs. They're used in surgery to reshape corneas, remove tumors, and cauterize blood vessels. They're used in manufacturing to cut steel, weld metal, and engrave surfaces with microscopic precision. They measure distances to the moon by bouncing laser pulses off reflectors left there by Apollo astronauts. They're used in military targeting systems, in scientific instruments, in supermarket checkout lines. All of it, every single application, works because of stimulated emission. Because a photon can encounter an excited atom and cause it to release an identical copy of itself. The difference between spontaneous and stimulated emission is profound. Spontaneous emission is random. Each atom emits its photon in a random direction at a random time, producing incoherent light like a light bulb or candle. Stimulated emission is organized. Every photon is identical. Same energy, same direction, same phase. The result is coherent light. A focused, intense beam where all photons march in perfect unison. This coherence makes lasers useful, allowing them to be focused to a pinpoint and carry information with extraordinary precision. And all of it comes back to the same fundamental interaction: a photon meeting an atom. But in this case, the photon isn't absorbed. Instead, it prompts the atom to release its stored energy as an identical photon. The original photon survives, and a new twin photon is born. The atom drops back to its ground state, having given up its extra energy. The universe now has one more photon than it did a moment ago, and that photon is a perfect clone of the one that triggered its creation. Now, let's step back and talk about what emission means on a larger scale. Because emission isn't just a laboratory phenomenon, it's happening everywhere in the universe, all the time, on scales that are almost unimaginable. Every star in the universe shines because of emission. Deep in a star's core, nuclear fusion reactions generate gamma-ray photons with enormous energy. These photons begin to travel outward through the star, but they don't make it very far before they encounter an atom and are absorbed. The atom gets excited, then emits a new photon, usually at a slightly different energy because of cascading. That new photon travels a short distance before it too is absorbed by another atom. This process repeats trillions upon trillions of times. Each absorption and re-emission changes the photon's direction and usually its energy. A gamma-ray photon born in the core of the Sun takes an estimated 100,000 to 200,000 years to reach the surface, bouncing from atom to atom the entire way. By the time photons finally escape from the Sun's surface, they've been absorbed and re-emitted so many times that their energy has been dramatically reduced. Think about what that journey looks like. A gamma-ray photon is born in the core at temperatures of about 15 million degrees Celsius. It travels less than a centimeter before it slams into another atom and is absorbed. That atom gets excited, and a fraction of a second later, it emits a new photon, usually at a slightly different energy and in a completely random direction. That new photon travels another centimeter or so before it too is absorbed. And so it goes, step by step, centimeter by centimeter. Each absorption and re-emission sends the photon in a new random direction. So instead of traveling straight outward, it wanders drunkenly through the star's interior, in what physicists call a random walk. The Sun is about 700,000 kilometers from core to surface. But because of this random walk, the photon's actual path is millions of times longer than a straight line. A journey that light could make in just over 2 seconds if it traveled straight becomes an odyssey lasting 100,000 years or more. And with each re-emission, the photon's energy tends to decrease slightly. One gamma ray becomes several X-ray photons. Those X-rays become ultraviolet photons. The ultraviolet photons eventually become visible light. By the time the energy finally reaches the surface, it has been divided and subdivided and transformed so many times that what emerges is a gentle flood of visible light and infrared warmth. What started as gamma rays in the core emerges as mostly visible light from the surface. The sunlight that warms your face is the end product of countless absorption and emission events deep inside a star. Emission is also what makes nebulae glow. A nebula is a cloud of gas in space, mostly hydrogen. When a hot, massive star is nearby, its intense ultraviolet radiation floods the nebula. Hydrogen atoms in the nebula absorb ultraviolet photons, their electrons jumping to high energy levels. Then the electrons cascade down, emitting photons at specific wavelengths. The most prominent emission is H-alpha, that 656 nanometer red glow from electrons falling from the third energy level to the second. This is why so many nebulae appear red in photographs. You're seeing hydrogen emission. The gas is absorbing ultraviolet photons from nearby stars and re-emitting them as visible red light through cascading. The nebula is essentially a giant fluorescent lamp powered by starlight. Other elements in the nebula contribute their own emission lines. Oxygen emits strongly in green. Nitrogen emits in red and blue. Sulfur emits in deep red. When you see those spectacular multicolored images of nebulae from space telescopes, each color represents a different element emitting photons at its own characteristic wavelengths as its electrons cascade down through their energy levels. This brings us to one of the most important concepts in all of astronomy: the difference between absorption spectra and emission spectra. These two types of spectra are complementary. They're two sides of the same coin, both created by the same fundamental interaction between photons and atoms, but observed under different conditions. An absorption spectrum is what you get when you look at a continuous source of light. like a star, through a cooler gas. The hot surface of the star emits light at all wavelengths, producing a smooth rainbow of color. But as that light passes through the cooler gas in the star's outer atmosphere or in an intervening gas cloud, atoms in the gas absorb photons at their specific characteristic energies. The result is a rainbow with dark lines at specific wavelengths. Each dark line corresponds to a specific transition in a specific atom. By reading these dark lines, astronomers can identify exactly which elements are present in the gas. An emission spectrum is what you get when you look directly at a hot, diffuse gas without a continuous background source. Instead of seeing a rainbow with dark lines, you see bright lines on a dark background. The gas is emitting photons at specific wavelengths as excited electrons drop down through their energy levels. Each bright line corresponds to the same transition that would produce a dark line in absorption. The wavelengths are identical, it's just the context that differs. In absorption, you're seeing which photons were removed from a continuous source. In emission, you're seeing which photons were released by an excited gas. Kirchhoff figured this out in 1859, and it remains one of the most powerful tools in all of science. Every element, every ion, every molecule has its own unique spectral fingerprint. And that fingerprint is the same whether you're looking at absorption or emission. The pattern of lines is identical because the underlying energy levels are the same. What changes is whether you're seeing those energy levels as gaps in a continuous spectrum or as isolated bright lines against darkness. This tool has allowed us to determine the composition of objects we can never touch. We know what the sun is made of. We know what the atmospheres of distant planets contain. We know the chemical makeup of galaxies billions of light years away. We've mapped the distribution of elements across the entire observable universe, and every single one of those measurements relies on the same thing. Photons being absorbed and emitted by atoms at very specific energies determined by the quantum mechanical structure of those atoms. Let me bring this all together. When an atom absorbs a photon and its electron jumps to a higher energy level, the story doesn't end there. The atom responds. It must respond because excited states are unstable. The electron falls back down, and when it does, it releases energy as a new photon. This emission can happen in one big jump, producing a photon with the same energy as the one that was absorbed, or it can happen in a series of smaller jumps, producing multiple photons of lower energy. The emitted photons fly off in random directions unless stimulated emission is involved, in which case they emerge as identical copies of a triggering photon. Spontaneous emission gives us the glow of hot gases, the light of nebulae, the shine of neon signs, and the flicker of flames. Cascading emission gives us fluorescence, the glow of black light posters, the brightness of whitened laundry, and the eerie light of fluorescent minerals. Stimulated emission gives us lasers, from the barcode scanner at the grocery store to the laser scalpel in the operating room to the fiber optic cables that carry the internet across continents. All of these phenomena, every single one, trace back to the same basic event. An electron in an atom dropping from a higher energy level to a lower one and releasing the energy difference as a photon. The energy of that photon is determined by the gap between the two levels. The type of emission, spontaneous or stimulated, determines whether the photon is random or coherent. And the path the electron takes, whether it drops in one jump or cascades through intermediate levels, determines whether you get one photon or many, at the original energy or at lower energies. The universe runs on this process. Stars pour photons into space through emission. Nebulae glow through emission. The aurora that shimmers above the poles of our planet is emission. Atoms in the upper atmosphere get excited by charged particles from the solar wind, and when their electrons drop back down, they emit photons at characteristic wavelengths. Green aurora comes from oxygen atoms emitting at about 557 nanometers. Red aurora comes from oxygen emitting at a different transition, about 630 nanometers. Purple and blue aurora comes from nitrogen. Every shimmering curtain of light in the polar sky is atoms releasing photons as their electrons cascade down from excited states. It's the same physics that makes a neon sign glow, the same physics that powers a laser, the same physics that lights a nebula thousands of light years away. Absorption and emission are the heartbeat of the photon-atom interaction. One is the inhale, the other the exhale. Together, they create the spectral fingerprints that let us read the composition of the universe from afar. They turn invisible light into visible light through fluorescence. They amplify light into coherent beams through lasers. They paint the sky with auroras and set nebulae ablaze with color. They are the reason we can see at all, because the light reaching your eyes right now is photons that were emitted by atoms, whether in a light bulb filament, an LED, a screen, or the sun. Every photon you have ever seen was born in an act of emission. An electron fell, and a photon was created. And every one of those photons carries the precise energy signature of the atomic transition that produced it. That signature is a message. It tells you which atom emitted it, which energy levels were involved, what element is present. The universe is constantly broadcasting information about itself through the photons its atoms emit. Every star, every gas cloud, every glowing material is sending out a coded signal in the form of spectral lines, telling anyone who knows how to read them exactly what the material is made of. We learned to read those signals. We built spectrographs and telescopes and detectors that can separate light into its component wavelengths and identify the spectral lines within. And through that ability, we've mapped the chemistry of the cosmos without ever leaving our planet. We know that the most distant galaxies contain the same elements found on Earth. Hydrogen, helium, carbon, oxygen, iron, the same atoms, following the same quantum rules, absorbing and emitting the same photon energies. The physics is universal. It works the same everywhere, in every galaxy, at every distance, at every point in time since atoms first formed in the cooling aftermath of the Big Bang. A hydrogen atom on Earth absorbs and emits at exactly the same wavelengths as a hydrogen atom in a galaxy 10 billion light years away. The rules haven't changed. The energy levels haven't shifted. The interaction between photons and atoms is one of the most reliable, most consistent, most universal processes in all of nature. And it all comes back to this. An electron in an excited state falls. A photon is born. The universe gains one more particle of light, carrying a message about the atom that created it, traveling at 300,000 kilometers per second toward whatever it encounters next. The atom settles back into its ground state, waiting for another photon to come along and start the cycle again. Absorption, emission, absorption, emission. An endless rhythm playing out in every atom in the universe, from the cores of stars to the cells of your body, right now, in this very moment, trillions of times over. So far, we've explored two possible outcomes when a photon meets an atom. The photon can be absorbed, vanishing entirely as it lifts an electron to a higher energy level. And the excited atom can emit a new photon when that electron falls back down. These are clean transactions. Energy in, energy stored, energy out. The photon's energy matches an allowed transition in the atom, and the exchange happens with perfect precision. But what happens when the photon's energy doesn't match? What happens when a photon arrives at an atom and its energy doesn't correspond to any allowed jump between electron energy levels? You might think the answer is simple. The photon just passes through. The atom ignores it. And in many cases, that's exactly what happens. But not always. There's a third possibility, a middle ground between full absorption and complete indifference. The photon can be scattered. It doesn't get absorbed. The electron doesn't make a lasting transition to a higher energy level. Instead, the photon interacts briefly with the atom and then leaves, deflected in a new direction. It's still a photon. It still exists. But something about it may have changed. And this process, scattering, is responsible for some of the most familiar and beautiful phenomena in your everyday life, including the color of the sky. Let's start with the most common type. Elastic scattering, which physicists often call Rayleigh scattering after the British physicist Lord Rayleigh, whose real name was John William Strutt. In the 1870s, Lord Rayleigh set out to answer a question that humans have been asking for thousands of years. Why is the sky blue? It seems like a simple question, but the answer is anything but simple. And it comes down to how photons interact with atoms and molecules when absorption isn't an option. Here's what happens. Sunlight enters Earth's atmosphere. Sunlight is white light, meaning it contains photons of all visible wavelengths, from deep red to violet and everything in between. These photons encounter the molecules in the atmosphere, primarily nitrogen and oxygen. Now, the energy of visible light photons doesn't match any of the allowed electronic transitions in nitrogen or oxygen molecules. These molecules can't absorb visible light. Their energy level gaps are too large. They would need ultraviolet photons to make their electrons jump. So visible light shouldn't interact with them at all. The atmosphere should be perfectly transparent to all colors of visible light equally. And the sky should appear either white from direct sunlight or black like space. But that's not what happens. And the reason is Rayleigh scattering. Even when a photon's energy doesn't match an allowed transition, the photon's electromagnetic field still interacts with the electrons in the molecule. The photon's oscillating electric field pushes and pulls on the electron cloud of the molecule, causing it to oscillate briefly. The molecule doesn't absorb the photon. The electron doesn't make a lasting jump to a higher energy level. But the electron cloud wobbles, vibrates, distorts for an instant. And that wobbling electron cloud acts like a tiny antenna. It radiates energy. It sends out a photon at the same energy, the same wavelength as the one that caused the wobble. But this re-radiated photon can go in any direction. The key insight, the thing Lord Rayleigh figured out, is that this process is not equally effective at all wavelengths. The amount of scattering depends very strongly on the wavelength of the photon. Specifically, shorter wavelengths are scattered far more than longer wavelengths. The relationship follows what physicists call an inverse fourth power law. If you halve the wavelength, the scattering increases by a factor of 16, 2 to the fourth power. This means that violet and blue light which have the shortest wavelengths in the visible spectrum, are scattered much more efficiently than red and orange light, which have the longest wavelengths. Blue light has a wavelength of about 450 nanometers. Red light has a wavelength of about 700 nanometers. The ratio is about 1 to 1.55, but because scattering goes as the inverse fourth power of wavelength, blue light is scattered roughly 6 times more than red light. That's a huge difference. When sunlight enters the atmosphere, blue photons get scattered in all directions far more efficiently than red photons. Red photons tend to continue straight through the atmosphere without being deflected. Blue photons bounce around, scattered from molecule to molecule, redirected in random directions across the sky. This is why the sky is blue. When you look up at any part of the sky that isn't the sun itself, you're seeing scattered light. Sunlight that entered the atmosphere heading in one direction and got bounced toward your eyes by molecules in the air. And because blue light is scattered so much more effectively than other colors, the scattered light reaching your eyes from across the sky is predominantly blue. Now you might ask, if scattering is even stronger for violet light, why isn't the sky violet? 2 reasons. Sunlight contains less violet than blue because the sun's emission spectrum drops off toward violet wavelengths, and human eyes are much more sensitive to blue than to violet. The physics favors violet, but our biology favors blue. So we see a blue sky. Rayleigh scattering also explains why sunsets are red and orange. When the sun is near the horizon, its light has to travel through much more atmosphere than when it's directly overhead. The path through the atmosphere might be 30 to 40 times longer at sunset than at noon. Over this extended path, the shorter wavelengths, blue and violet, are almost completely scattered away. They get bounced out of the beam in all directions long before the light reaches your eyes. What's left is the longer wavelength light, red and orange. These colors survive the long journey through the atmosphere because they scatter so much less. By the time the sunlight reaches you at sunset, it's been stripped of its blue and violet components, leaving behind a warm red and orange glow. This is worth pausing on because it's entirely different from absorption. In absorption, the photon ceases to exist. Its energy is transferred to an electron that jumps to a higher level. In Rayleigh scattering, the photon is not destroyed. No electron makes a lasting transition. The photon simply changes direction. It bounces off the molecule like light bouncing off a mirror, except the direction of the bounce is random, and the photon leaves with the same energy it arrived with. That's what makes it elastic scattering. No energy is gained or lost. The photon's wavelength doesn't change, only its direction changes. The molecule returns to exactly the same state it was in before the encounter. Nothing about the molecule has permanently changed. This distinction is crucial. Absorption removes photons from the universe, at least temporarily. They get destroyed. Scattering doesn't remove them. It redirects them. The photons still exist. They still carry the same energy. They've just been sent on a new path. This is why the sky is bright during the day. Scattered photons haven't been destroyed. They've been redistributed across the sky, creating a diffuse blue glow that illuminates everything, even in shadow. Rayleigh scattering operates whenever the scattering particles are much smaller than the wavelength of light. Atmospheric molecules are a few angstroms across, far smaller than the wavelengths of visible light, which are hundreds of nanometers. When the particles become comparable in size to the wavelength, a different kind of scattering takes over, called mi-scattering, which scatters all wavelengths more equally. This is why clouds are white. Water droplets in clouds are much larger than the wavelength of visible light, so they scatter all colours roughly equally. The mixture of all colours scattered equally produces white. Now let's move to a very different kind of scattering, one that involves a real energy exchange between the photon and the particle it encounters. This is inelastic scattering, and the most important example at the atomic level is Compton scattering. Compton scattering was discovered experimentally by the American physicist Arthur Holly Compton in 1923. Compton was shooting X-ray photons at a target made of graphite and measuring the wavelengths of the X-rays that bounced off. He found something unexpected. The scattered X-rays had a longer wavelength than the incoming X-rays. Longer wavelength means lower energy. The photons had lost energy during the scattering process, and the amount of energy they lost depended on the angle at which they scattered. Here's what was happening. When a high-energy photon like an X-ray collides with an electron, it's not a gentle wobble like in Rayleigh's scattering. It's a more violent interaction. The photon transfers some of its energy and momentum to the electron, knocking it loose, or at least giving it a significant kick. The electron recoils, carrying away kinetic energy. The photon bounces off in a new direction, but because it gave some of its energy to the electron, it now has less energy than before. Less energy means longer wavelength. The photon has been downgraded. This is fundamentally different from Rayleigh scattering. In Rayleigh scattering, the photon keeps all its energy. In Compton scattering, the photon loses energy to the electron. The interaction is inelastic. Energy has been transferred from the photon to the electron. The photon survives, but it's been diminished. It has been shifted to a longer wavelength, a lower frequency, a lower energy, and the electron has gained that energy as kinetic energy, recoiling from the impact. Compton scattering is most significant for high-energy photons, X-rays and gamma rays interacting with loosely bound or free electrons. At the lower energies of visible light, Compton scattering is negligible. The photons simply don't have enough momentum to kick electrons around significantly. But at X-ray and gamma ray energies, Compton scattering becomes a dominant process. It's one of the main ways that high-energy radiation interacts with matter. Compton's discovery was enormously important for physics because it provided direct evidence that photons carry momentum. Before Compton's experiment, the idea that light was made of particles, photons, was still controversial. Many physicists accepted that light was quantized, that it came in packets of energy, but the idea that these packets also carried momentum like a physical object was harder to swallow. Compton showed that when a photon bounces off an electron, the physics of the collision obeys the same conservation of energy and conservation of momentum rules that apply to billiard balls on a pool table. The photon acts like a particle with real momentum, not just a wave. This was powerful confirmation of the particle nature of light. The amount of energy the photon loses in Compton scattering depends on the angle at which it scatters. If the photon barely glances off the electron, it loses very little energy, and its wavelength changes only slightly. If the photon bounces almost straight backward, it loses the maximum amount of energy, and its wavelength shift is largest. Compton worked out the exact mathematical relationship between the scattering angle and the wavelength change, and his formula matched the experimental data perfectly. This formula, now known as the Compton scattering equation, became one of the foundational results of quantum physics. There's one more type of scattering that deserves attention, and it operates at a level between Rayleigh and Compton. It's called Raman scattering, named after the Indian physicist C. V. Raman, whose full name was Chandra Sekhara Venkata Raman. He discovered this effect in 1928, and it earned him the Nobel Prize in Physics in 1930. Raman scattering is subtle, it's rare, and it reveals information about molecules that no other technique can easily provide. In normal Rayleigh scattering, a photon bounces off a molecule with the same energy, and the molecule returns to its original state. But in Raman scattering, the molecule doesn't return to exactly its original state. It ends up in a slightly different vibrational or rotational state. This change means energy has been exchanged between the photon and the molecule. The photon either lost a little energy to the molecule or gained a little from it. If the photon loses energy to the molecule, the scattered photon has a longer wavelength than the incoming photon. This is called Stokes-Raman scattering. The molecule absorbed a small amount of energy and is now vibrating more energetically. If the molecule was already vibrating before the interaction and gives some of that vibrational energy to the photon, the scattered photon comes out with more energy, a shorter wavelength. This is called anti-Stokes-Raman scattering. In either case, the energy change is small, much smaller than the energy of the photon itself. The photon doesn't change from visible to infrared or from blue to red. The wavelength shift is tiny, but it's measurable. And crucially, the amount of the shift tells you about the vibrational frequencies of the molecule. Raman scattering is extraordinarily rare. For every 10 million photons that undergo Rayleigh scattering from a molecule, only about 1 photon will undergo Raman scattering. It's a needle in a haystack phenomenon. But modern instruments are sensitive enough to detect it, and Raman spectroscopy has become one of the most powerful analytical tools in chemistry, biology, and material science. Why is Raman scattering useful? Because the vibrational frequencies of a molecule depend on the masses of its atoms and the strengths of the bonds between them. Every molecule has a unique set of vibrational modes, like a unique set of musical notes. By measuring the Raman shifts, the small wavelength changes in scattered photons, scientists can identify the molecule. It's like a molecular fingerprint, completely distinct for every chemical compound. You can identify substances without touching them, without preparing samples, without chemical tests. Just shine a laser on a material, collect the scattered light, look for the tiny wavelength shifts, and you know what you're looking at. This technique is used in art restoration to identify pigments without damaging paintings, in forensics to analyze trace evidence, in pharmaceutical manufacturing to verify drug purity, and in geology to identify minerals. It's also being developed for medical applications where a non-invasive scan could identify abnormal tissue. Now, let's bring these 3 types of scattering together and understand what they have in common and where they differ. All 3 involve a photon encountering a particle and being redirected. In none of these cases does the atom or molecule make a lasting electronic transition to a higher energy level. The electron doesn't permanently jump to a higher rung on the energy ladder the way it does in true absorption. Instead, the interaction is briefer, less committed. The photon engages with the particle and then leaves. In Rayleigh scattering, the photon leaves with the same energy. The interaction is elastic. Nothing changes except the photon's direction. This is the most common type and is responsible for the blue sky, red sunsets, and the general diffusion of light through any transparent medium. In Compton scattering, the photon leaves with less energy. The interaction is inelastic. The photon has been knocked down in energy, and the electron it hit has gained kinetic energy. This is important for high-energy radiation interacting with matter. In Raman scattering, the photon leaves with slightly different energy, either a little less or a little more. The molecule's vibrational state has changed. This is the rarest type but provides the richest chemical information. All three are distinct from absorption. In absorption, the photon is destroyed and the electron makes a lasting quantum jump. In scattering, the photon survives and no lasting electronic transition occurs. This distinction is fundamental, and it explains one of the most basic properties of matter: transparency. Why are some materials transparent and others opaque? Why can you see through glass, but not through a brick wall? Why is water transparent to visible light, but absorbs infrared? The answer lies in the interaction between photons and the atoms or molecules in the material. A material is transparent to a particular wavelength of light when neither absorption nor significant scattering occurs. This means the photon's energy doesn't match any allowed electronic transition in the material's atoms or molecules, and the material's structure doesn't cause significant scattering. The photons pass through unmolested, and you can see through the material. Glass is transparent to visible light because the energy gaps between electron levels in the silicon and oxygen atoms that make up glass are too large for visible light photons to bridge. Visible photons don't have enough energy to excite electrons in glass. They pass through. But ultraviolet photons do have enough energy, which is why ordinary glass blocks most ultraviolet light. The same glass that's transparent to blue light is opaque to ultraviolet. The difference is entirely about whether the photon's energy matches an allowed transition. Water is transparent to visible light for the same reason. The molecular structure of water has energy gaps that don't correspond to visible wavelengths. But water does absorb infrared light because infrared photons have the right energy to excite vibrational modes in water molecules. The molecules vibrate more energetically, which we perceive as heat. This is why infrared radiation warms water and why microwave ovens work. Water molecules are polar, meaning they have a positively charged end and a negatively charged end. The oscillating electric field of the microwave radiation forces these polar molecules to rapidly reorient themselves, trying to align with the alternating field billions of times per second. This constant molecular jostling creates friction between neighboring molecules, and that friction generates heat. The microwave frequency is deliberately chosen so that the radiation penetrates several centimeters into food before being fully absorbed, allowing the interior to cook rather than just the surface. Metals are opaque because they have free electrons. Electrons that aren't bound to any particular atom but can move freely throughout the metal. These free electrons can absorb photons of almost any energy in the visible range because they don't have the same quantized energy level restrictions as bound electrons. The free electrons soak up the incoming photons, which is why light doesn't pass through a sheet of metal. The metal reflects most of the visible light that hits it, which is why metals are shiny. The free electrons absorb the incoming photons and immediately re-emit them back outward, acting like a mirror. Think about how remarkable this is. The difference between a material being transparent and opaque, between being see-through and solid-looking, comes down entirely to how the photons interact with the atoms in that material. Whether a photon gets absorbed, scattered, reflected, or transmitted depends on the energy of the photon and the quantum mechanical structure of the atoms and molecules it encounters. The same material can be transparent to one wavelength and opaque to another. Your body, for example, is mostly opaque to visible light. You can't see through your hand. But X-rays pass through soft tissue relatively easily because flesh is made of light elements: carbon, hydrogen, oxygen, and nitrogen. These atoms have relatively few electrons and low binding energies, so they don't absorb X-ray photons very efficiently. Most X-ray photons slip through without being captured. Bone, however, contains heavier elements like calcium and phosphorus. Heavier atoms have more electrons and higher binding energies, making them far more effective at absorbing X-ray photons. This is why X-ray images show your skeleton. The bone absorbs the X-rays and casts a shadow. The soft tissue lets most of them pass, appearing nearly transparent. The same hand that blocks visible light is transparent to X-rays. The difference is, once again, the energy of the photon. Let me return to something I mentioned earlier, because it connects scattering to the larger story of how photons interact with atoms. When we look at the spectrum of a star, we see both the effects of absorption and scattering at work. Photons leave the star's surface traveling outward. As they pass through the cooler outer layers of the star's atmosphere, some photons get absorbed by atoms, producing dark absorption lines, but other photons get scattered, especially by free electrons in the star's hot outer atmosphere. This scattering broadens and blurs spectral lines, makes the star appear slightly larger than its physical surface, and creates a diffuse halo of light around the star. In the interstellar medium, the thin gas and dust between stars, scattering plays an enormous role. Tiny dust grains, each perhaps 1,000th of a millimeter across, scatter starlight in a way similar to Rayleigh scattering, but modified by the size and composition of the grains. Shorter wavelengths of starlight are scattered more than longer wavelengths. This means that when we look at a distant star through a dust cloud, the star appears redder than it actually is. The blue light has been scattered away. Astronomers call this interstellar reddening, and they have to correct for it whenever they study distant objects. The dust between us and the object has selectively removed shorter wavelengths from the light, making everything look redder and dimmer than it truly is. This is not the same as a sunset, although the underlying principle is similar. In a sunset, atmospheric molecules scatter blue light, letting red light through. In interstellar reddening, dust grains scatter blue light, letting red light through. Different particles, different scales, but the same basic physics. Shorter wavelengths interact more strongly with small particles and get redirected away from the line of sight. Scattering also connects to a puzzle that troubled early astronomers. If the universe were infinite and filled with stars, every line of sight should eventually hit a star, and the sky should blaze with light. This puzzle, known as Olbers's paradox, is resolved primarily by the finite age and expansion of the universe, meaning light from the most distant stars hasn't reached us yet, and distant light is redshifted. Scattering and absorption by interstellar dust further attenuates starlight, contributing to the dark night sky. Scattering reveals something deep about the nature of the photon-atom interaction. Absorption is all or nothing. The photon either has the right energy and is swallowed completely, or it doesn't and passes through. But scattering is more subtle. It allows photons that don't match any absorption line to still interact with matter. The interaction is gentler, briefer, and doesn't involve a lasting energy level change, but it's real. It has measurable, visible consequences. The blue sky overhead is proof that even when a photon can't be absorbed, it can still be influenced by the atoms and molecules it encounters. It can be nudged, deflected, redirected. The atom doesn't capture it, but the atom doesn't ignore it either. This matters because it fills in a crucial piece of the overall picture. When a photon encounters an atom, there aren't just two outcomes, absorption or nothing. There are many possible outcomes on a spectrum from full absorption to gentle deflection to complete indifference. The outcome depends on the energy of the photon, the structure of the atom or molecule, and the type of interaction that's possible. Scattering occupies the space between absorption and transparency. It allows matter to influence light without destroying it. And this brings us to a deeper point about how the universe works. Light and matter are constantly interacting. Every photon traveling through space is potentially subject to scattering by every atom and molecule it passes near. Most of the time, the interaction is too weak to matter. The photon sails past without being significantly deflected. But over long distances, through dense media, or at wavelengths where scattering is strong, these gentle deflections add up. They shape the light we receive from distant objects. They determine the colors of our sky. They make clouds white and sunsets red. They cause distant stars to appear dimmer and redder than they really are. They even affect the cosmic microwave background radiation, the oldest light in the universe, which has been scattered and rescattered over billions of years. Scattering is the quiet sibling of absorption. It doesn't have the drama of a photon being destroyed or an electron being ejected. It doesn't produce the vivid spectral lines that make absorption and emission so useful for identifying elements. But it's everywhere. It's constant. It's the background interaction, the default way photons and matter acknowledge each other's presence when no stronger interaction is available. And without it, the world would look completely different. The sky would be black during the day. Shadows would be pitch dark with no scattered light to fill them. Clouds wouldn't exist as we know them. The diffuse, soft, ambient light that fills our world and makes it beautiful would simply not be there. Every time you look at the blue sky, you're seeing scattering. Every sunset is scattering. Every white cloud is scattering. The soft glow of light on a foggy morning is scattering. The shimmer of light in a glass of water is scattering. The way the world doesn't vanish into harsh light and absolute shadow, but instead exists in a rich tapestry of color and tone and softness, that's scattering. That's trillions of photons being gently redirected by the atoms and molecules around you, filling in the gaps, softening the edges, painting the atmosphere with diffuse light. And none of it involves absorption. None of it involves photons being destroyed or electrons jumping to higher levels. It's a fundamentally different interaction, one where the photon survives, where the atom returns to its original state, and where the only thing that changes is the direction the photon travels. It's the gentlest thing a photon can do to an atom, but in its own quiet way, it transforms the world. We've now seen 3 things a photon can do when it encounters an atom. It can be absorbed, vanishing completely as it lifts an electron to a higher energy level. It can trigger emission, prompting an excited atom to release a new photon. And it can be scattered, bouncing off an atom or molecule in a new direction without being destroyed. Each of these outcomes depends on the photon's energy and the atom's internal structure. But there's one more possibility. the most violent one, the one that doesn't just rearrange an atom's electrons but tears them away entirely. This is ionization. And it happens when a photon arrives with so much energy that instead of lifting an electron to a higher rung on the energy ladder, it rips the electron off the ladder completely, ejecting it from the atom altogether. In absorption, the electron moves from one allowed energy level to another. It's still bound to the atom. It's still part of the atom's structure. It's just been promoted to a higher state. In ionization, the electron is given so much energy that it escapes the atom's gravitational grip entirely. It flies away as a free electron, no longer attached to any nucleus. And the atom, now missing an electron, is no longer electrically neutral. It's become an ion, a positively charged particle. The photon has done something irreversible. It hasn't just excited the atom, it has fundamentally changed it. Think back to the energy level ladder. The rungs represent allowed energy states. The lowest rung is the ground state. Higher rungs are excited states. But the ladder doesn't go up forever. There's a top. Above a certain energy, the electron is no longer bound to the atom. The energy required to reach this point is called the ionization energy or binding energy. If a photon arrives with energy equal to or greater than this binding energy, the electron doesn't jump to a higher rung. It leaves the ladder entirely. It escapes the atom. And here's the critical detail. Any energy the photon carries beyond the minimum needed for ionization doesn't just vanish. It becomes kinetic energy of the ejected electron. The electron flies away with speed. The more energy the photon had above the ionization threshold, the faster the ejected electron moves. If the photon had exactly the binding energy, the electron barely escapes, drifting away with almost no speed. If the photon had twice the binding energy, the electron rockets away with considerable kinetic energy. The excess is transferred directly and completely. This phenomenon has a name that almost everyone has heard, but very few truly understand: the photoelectric effect. And its explanation earned Albert Einstein the Nobel Prize in Physics in 1921. Not for relativity, which most people associate with Einstein. Not for any of his other groundbreaking work. The Nobel Committee gave him the prize specifically for explaining the photoelectric effect, because this explanation did something that changed physics forever. It proved that light is quantized. That light comes in discrete packets of energy, photons, each carrying a specific amount of energy determined by its frequency. And this was the foundation on which all of quantum mechanics was built. Let me tell you the story. In 1887, the German physicist Heinrich Hertz was experimenting with electromagnetic waves. He noticed something odd. When ultraviolet light fell on a metal surface, electricity was produced. Electrons were being ejected from the metal. This was the photoelectric effect in its raw, unexplained form. Hertz didn't understand why it happened. He just observed it. Over the following years, other physicists studied this effect carefully. Philipp Lenard, working around 1902, made precise measurements and discovered several things that were deeply puzzling. First, there was a threshold frequency. Below a certain frequency of light, no electrons were ejected from the metal, no matter how bright the light was. You could shine an incredibly intense beam of red light on a metal surface for hours, days, weeks, and not a single electron would be ejected. Not one. But if you shone a dim beam of ultraviolet light on the same surface, electrons flew out immediately. This made absolutely no sense under the classical wave theory of light. If light were a continuous wave, then brighter light should carry more energy. Shining a brighter red light should eventually deliver enough energy to knock electrons loose. It would just take longer for the energy to build up. But that's not what happened. Below the threshold frequency, no amount of brightness made any difference. The electrons stayed put. Second, Leonard found that above the threshold frequency, the electrons were ejected immediately. There was no delay. Even in extremely dim light, as long as the frequency was above the threshold, electrons came out instantly. If light were a wave delivering energy continuously and gradually, there should have been a detectable delay while the electron accumulated enough energy from the wave to escape. But there was no delay at all, not even a fraction of a second. The electrons came out the instant the light arrived. Third, the kinetic energy of the ejected electrons depended on the frequency of the light, not its brightness. Higher frequency light produced faster electrons. Brighter light at the same frequency didn't make the electrons faster. It just produced more of them. More photons meant more ejection events. But each individual event produced an electron with the same kinetic energy regardless of how many other photons were hitting the surface. These observations were completely inexplicable under the wave model of light. They contradicted everything physicists thought they knew about how light delivers energy to matter. The experiment sat as unsolved puzzles for years, taunting the physics community. Then, in 1905, Einstein published his explanation, and it was breathtakingly simple. Light, Einstein said, is not a continuous wave. It comes in discrete packets, quanta, which we now call photons. Each photon carries a specific amount of energy that depends on its frequency. Higher frequency means more energy per photon. Lower frequency means less. When a photon hits a metal surface, it interacts with a single electron. One photon, one electron. The photon delivers all of its energy to that one electron in a single instant. If the photon's energy is greater than the binding energy holding the electron in the metal, the electron is ejected. If the photon's energy is less than the binding energy, the electron can't escape. It doesn't matter how many low-energy photons hit the surface. Each one interacts with its own electron, and none of them individually carries enough energy to free it. 1,000 weak photons can't combine their energy to eject one electron. Each photon acts alone. This explained everything. The threshold frequency exists because below that frequency, each individual photon doesn't carry enough energy to overcome the binding energy. No amount of brightness helps because brightness means more photons, but each photon is still too weak. Above the threshold, electrons come out instantly because each photon delivers all its energy at once. There's no build-up, no gradual accumulation. The energy arrives in a single packet. The kinetic energy of the ejected electrons depends on the photon's frequency, because the excess energy above the binding threshold goes directly into the electron's speed. Higher frequency means more excess energy, which means faster electrons. Brighter light means more photons, which means more electrons ejected. But each individual electron has the same kinetic energy because each was freed by one photon with the same frequency. This principle doesn't just explain a laboratory curiosity, it's the foundation of one of the most important technologies of the modern world. Solar cells. Every photovoltaic panel on every rooftop and solar farm on Earth works because of the photoelectric effect. Photons from the sun strike a semiconductor material, usually silicon. If the photon's energy exceeds a threshold called the band gap energy, it promotes an electron within the silicon crystal from a bound state to a mobile state. The electron doesn't leave the material the way it does in Einstein's original metal surface experiment. Instead, it moves into a higher energy condition inside the crystal where it can flow through a circuit, generating electricity. If the photon's energy is below the band gap threshold, the electron can't make the jump and no electricity is produced. This is why solar cells don't work equally well with all wavelengths of light. Infrared photons from sunlight mostly lack the energy to free electrons in silicon. They pass through or generate heat. Visible and ultraviolet photons have enough energy to kick electrons loose. The entire solar energy industry, a technology generating hundreds of gigawatts of electricity worldwide, rests on Einstein's insight from 1905. Photons are particles. Each one carries a specific energy, and when that energy exceeds the threshold needed to free an electron, the electron escapes. One photon, one electron, one tiny pulse of current. Multiply that by the trillions of photons striking a solar panel every second, and you get enough electricity to power a home. Einstein's explanation was elegant, complete, and correct, but was also radical. It meant that light, which everyone had thought was a wave, had particle-like properties. Each photon was a discrete entity carrying a specific energy, interacting with individual electrons one at a time. This was one of the founding insights of quantum mechanics, the idea that energy is not continuous but comes in discrete packets. And it all came from understanding what a photon does to an atom when it carries enough energy to eject an electron. Now let's think about what happens after ionization. The atom has lost an electron. It's now a positively charged ion, and the ejected electron is flying through space as a free particle. Both of these products, the ion and the free electron, behave very differently from a neutral atom and a bound electron. The ion, being positively charged, can interact with other charged particles in ways that neutral atoms can't. It can be attracted to negatively charged particles and repelled by positive ones. In a gas, ions can recombine with free electrons, capturing them and becoming neutral atoms again. When this recombination happens, the electron cascades down through the atom's energy levels, emitting photons at each step. This recombination emission is one of the primary sources of light in many astronomical objects. The free electron, meanwhile, can collide with other atoms, transferring energy and potentially ionizing them in a chain reaction. One ionization creates a free electron that causes another, which causes another. This cascade is what makes high-energy radiation dangerous to living tissue. A single gamma-ray photon can trigger a chain of ionization events, breaking chemical bonds and damaging the delicate molecular machinery of living cells. This is why radiation is harmful. It is not the energy itself that causes biological damage. The total energy in a dose of gamma rays might be tiny, far less than the energy in a cup of warm tea. What makes it dangerous is the way that energy is delivered. Each gamma ray photon carries enough energy to ionize atoms in biological molecules. When atoms in a strand of DNA are ionized, the chemical bonds holding the molecule together can break. Picture the DNA molecule as a twisted ladder. The rungs of that ladder are pairs of chemical bases held together by bonds between atoms. Each bond depends on electrons being shared between atoms in a precise arrangement. When a gamma ray photon ionizes one of those atoms, it rips an electron out of that arrangement. The bond breaks. A rung on the ladder snaps. Sometimes the cell can repair the damage, stitching the broken rung back together with specialized molecular machinery. But if multiple rungs break close together, or if the break occurs at a critical point in the genetic code, the repair may fail. The instructions encoded in that stretch of DNA become garbled or lost. The DNA gets damaged. If the damage is extensive enough, or if it hits critical locations in the genetic code, the cell might malfunction, die, or become cancerous. This is also why there's a fundamental difference between being exposed to a warm lamp and being exposed to an ultraviolet lamp. A warm lamp emits mostly infrared radiation. Each infrared photon carries very little energy, not enough to ionize anything. The photons are absorbed by molecules and converted to heat. You get warm. An ultraviolet lamp emits photons with much more energy per photon. These photons can ionize atoms in your skin cells. They can break chemical bonds in DNA. They cause sunburn, and over time, they increase the risk of skin cancer. The total amount of energy might be similar between the two lamps. But the way that energy is packaged in many weak photons versus fewer strong photons makes all the difference. It's the energy per photon that matters, not the total energy. Earth's atmosphere protects us from most of the ionizing radiation that comes from space. The sun emits enormous quantities of ultraviolet radiation, along with X-rays from its hot corona, especially during solar flares. Beyond our solar system, distant cosmic sources like supernovae and the violent cores of other galaxies produce gamma rays that also stream through space. If all of this radiation reached the surface, life as we know it would be impossible, but the atmosphere acts as a shield. Ozone in the upper atmosphere absorbs most of the ultraviolet radiation, particularly the most energetic UVC and UVB wavelengths. Nitrogen and oxygen molecules absorb X-rays and gamma rays. By the time sunlight reaches the surface, most of the ionizing radiation has been filtered out. What reaches us is mostly visible light and some UVA, which is the least energetic type of ultraviolet. This filtering creates a remarkable structure in the upper atmosphere, the ionosphere. This is a region stretching from about 60 to 1,000 kilometers above Earth's surface, where the atmosphere is partially ionized. Up there, the atmosphere is thin enough that ultraviolet and X-ray photons from the sun can reach the gas molecules before being absorbed. These photons ionize nitrogen and oxygen molecules, knocking electrons free and creating a layer of ions and free electrons. This ionized layer has special properties. It can reflect radio waves, which is why AM radio signals can travel over the horizon by bouncing off the ionosphere. It can also interfere with radio communications during solar storms, when increased solar radiation produces more ionization than usual. The ionosphere exists because of the photoelectric effect on a planetary scale. Photons from the sun arrive with enough energy to ionize atmospheric molecules, and the result is a permanent shell of ionized gas surrounding our planet. At night, when the sun isn't shining on a given region, the ionosphere partially recombines, with ions and electrons reuniting. In the morning, when sunlight returns, the ionization builds up again. This daily cycle of ionization and recombination has been happening for billions of years, driven entirely by photons doing one specific thing to atoms: ejecting electrons. Ionization also shapes the structure of the universe on much larger scales. In the space between stars, ultraviolet radiation from hot, massive stars ionizes the surrounding hydrogen gas. A hot star with a surface temperature of 30,000 degrees or more pours out ultraviolet photons energetic enough to ionize hydrogen atoms. The hydrogen around such a star becomes ionized, forming what astronomers call an H2 region. These are some of the most beautiful objects in the cosmos. The Orion Nebula, the Eagle Nebula, the Carina Nebula, all of them are H2 regions. Enormous clouds of hydrogen gas ionized by the ultraviolet radiation of hot young stars embedded within them. The boundary of an H2 region is sharp. Inside the boundary, the gas is ionized. Hydrogen atoms are being hit by ultraviolet photons that rip their electrons away. The free electrons eventually recombine with hydrogen ions, cascading down through the energy levels and emitting photons at specific wavelengths. This recombination emission is what makes the nebulae glow. You're seeing atoms being ionized and then recombining over and over in a constant cycle driven by starlight. Outside the boundary, the ultraviolet photons have all been used up. They've been absorbed by hydrogen atoms on their way out from the star, and none are left to ionize atoms farther away. The gas beyond the boundary remains neutral, cold, dark, and invisible. The size of an H2 region depends on how luminous the central star is. A more luminous star produces more ultraviolet photons, which can ionize a larger volume of gas before being used up. The most massive stars, those with 50 or 100 times the mass of the Sun, can ionize regions hundreds of light years across. These enormous glowing bubbles of ionized gas are some of the most spectacular structures in the galaxy, and they exist entirely because of the photoelectric effect. Photons with enough energy to exceed the ionization threshold of hydrogen, doing exactly that to every atom they encounter until there are no more photons left. Now, let's tie all four parts of our story together, because we've now covered every major thing a photon can do to an atom, and they're all connected by one central principle: absorption. A photon arrives with energy that exactly matches the gap between two allowed energy levels in an atom. The photon is destroyed. The electron jumps to a higher level. The atom is excited. Emission. An excited atom releases its stored energy. The electron drops to a lower level. A new photon is born with energy equal to the gap the electron fell across. This can happen spontaneously or through stimulated emission. Scattering. A photon interacts with an atom or molecule, but the electron doesn't make a lasting transition. The photon is redirected. In elastic scattering, it keeps the same energy. In inelastic scattering, it gains or loses a small amount. Ionization. A photon arrives with energy greater than the binding energy of an electron. The electron is ejected from the atom entirely. The atom becomes an ion. Any excess photon energy becomes kinetic energy of the free electron. 4 outcomes, 4 fundamentally different results. And what determines which one happens is almost always the same thing. The energy of the photon compared to the energy level structure of the atom. A photon with energy matching an allowed transition gets absorbed. A photon with energy not matching any transition might be scattered. A photon with energy exceeding the ionization threshold kicks the electron out completely. The atom doesn't choose. The photon doesn't decide. The outcome is determined by the physics of the encounter, by the precise energy the photon carries, and the precise quantum architecture of the atom it meets. This single interaction, photon meets atom, is the most fundamental event in all of optics, chemistry, and a vast portion of astrophysics. It's the reason you can see. The light reaching your eyes right now consists of photons that were emitted by atoms in whatever you're looking at. Whether that's a screen emitting photons from electrically excited atoms, or a lamp whose heated filament is radiating photons, or sunlight that bounced off an object before reaching your retina, every act of vision is the final step in a chain of photon-atom interactions that started somewhere, maybe in a star, maybe in a light bulb, maybe in a chemical reaction, and ended with photons being absorbed by molecules in the retina of your eye. It's the reason chemistry works. Chemical bonds form and break because electrons rearrange themselves between atoms. Photons can trigger these rearrangements by exciting electrons, by ionizing atoms, or by providing the energy needed to overcome activation barriers in chemical reactions. Photosynthesis, the process that supports almost all life on Earth, begins with a photon being absorbed by a chlorophyll molecule in a leaf. That single absorption event starts a chain of chemical reactions that converts carbon dioxide and water into sugar and oxygen. Every plant, every tree, every blade of grass is powered by photon absorption. And every animal that eats those plants is indirectly powered by the same thing. The food chain on Earth is ultimately a photon-atom interaction chain, starting with sunlight hitting chlorophyll. It's the reason stars shine. Deep in the cores of stars, nuclear fusion creates gamma-ray photons. Those photons are absorbed and re-emitted billions of times as they work their way outward through the star. Each absorption and emission changes the photon's energy and direction. By the time the photons escape from the surface, they've been transformed from gamma rays into visible light. The light of every star in the sky is the end product of trillions of photon-atom interactions happening inside that star right now. It's the reason we know what the universe is made of. Absorption and emission spectra, the fingerprints created by photons interacting with specific atoms at specific energies, have allowed us to determine the chemical composition of stars, nebulae, galaxies, and the intergalactic medium. We've never visited another star. We've never collected a sample of gas from a nebula. But we know exactly what they're made of because the photons they send us carry coded information about every atom they've interacted with. It's the reason some radiation is dangerous and other radiation is harmless. The difference between visible light and gamma rays is just energy per photon. Visible light photons don't carry enough energy to ionize atoms in your body. They're safe. Gamma ray photons carry enough energy to rip electrons from atoms, break chemical bonds, and damage DNA. They're deadly. Same interaction, same physics, but the energy of the photon changes the outcome from harmless to lethal. And it's the reason the sky is blue, sunsets are red, glass is transparent, metals are shiny, nebulae glow, auroras shimmer, lasers work, solar cells generate electricity, and X-ray machines see through your skin to image your bones. Every single one of these phenomena comes back to the same thing. A photon encountering an atom and the outcome being determined by the photon's energy and the atom's quantum structure. There's something profound about this. The entire visible universe, everything you see when you look around, is a product of photon-atom interactions. You don't see atoms directly. What you see is the photons that atoms have emitted, reflected, scattered, or transmitted toward your eyes. Your entire visual experience of reality is mediated by photons. And those photons behave the way they do because of how they interact with atoms. The colors, the brightness, the transparency and opacity of materials, the glow of stars and nebulae, the blue of the sky, all of it is photons and atoms doing their quantum dance. When a single photon meets a single atom, the event seems small, inconsequential. One particle of light encountering one tiny building block of matter. But multiply that event by the trillions upon trillions of times it happens every second, in every star, in every gas cloud, in every molecule in your body, in every leaf on every tree, in every object that reflects or absorbs or emits light anywhere in the universe. And you realize that this one interaction is the engine that drives much of the physical world. It's how the universe communicates. It's how energy moves from place to place. It's how matter reveals its identity. It's how information travels across billions of light years of empty space. A photon leaves a distant star, travels through the void for years or centuries or millennia, and arrives at an atom in a telescope on Earth. That atom absorbs the photon, and we learn something about a star we'll never visit. The photon carried a message encoded in its energy, a message about the atom that created it, and the atom that received it decoded that message simply by absorbing it. The next time you step outside and feel sunlight on your face, remember what's actually happening. Photons that were born in nuclear fusion reactions deep inside the sun, that fought their way outward through hundreds of thousands of years of absorption and re-emission, that finally escaped from the sun's surface and traveled 150 million kilometers across empty space in about 8 minutes. Those photons are now arriving at the atoms in your skin. Some are being absorbed, their energy warming your cells. Some are being scattered by molecules in the air, painting the sky blue above you. Some are being absorbed by chlorophyll in the grass beneath your feet, powering the chemistry of life. Some are being reflected by the surfaces around you into your eyes, letting you see the world. All of it is the same interaction. A photon arrives at an atom. The atom's quantum structure determines what happens next. The photon might be absorbed. It might be scattered. It might ionize the atom. Or it might pass through entirely, continuing its journey until it meets an atom whose energy levels are a match. This is what a photon really does to an atom. It doesn't just hit it. It speaks to it. In a language of energy, written in the grammar of quantum mechanics, it asks a question. Does your structure match my energy? And the atom answers. Sometimes the answer is yes, and the photon is absorbed. Sometimes the answer is almost, and the photon is scattered. Sometimes the answer is more than enough, and an electron is torn free. And sometimes the answer is no, and the photon passes through as if the atom weren't there at all. But every encounter, every question and answer follows the same rules. Rules that were written into the fabric of reality at the very beginning. Rules that govern everything from the light of the most distant galaxy to the glow of a candle flame on your table tonight. These rules are not arbitrary. They are the deepest description we have of how light and matter coexist in this universe. And they are beautiful. Not beautiful in a vague poetic sense, but beautiful in the way a perfectly balanced equation is beautiful. In the way a single principle can explain 1,000 different phenomena. In the way that the simplest possible interaction, one photon meeting one atom, can build up through repetition and variation into everything you see, everything you feel, and everything you know about the cosmos.